As part of the nuclear chemistry chapter, I want to work some half-life problems with you. Let's start off just defining that term half-life because sometimes it can be confusing. Half-life is the amount of time it takes for half of a sample or half of the atoms in a sample to decay. Now when I say decay, I don't mean that they disappear or disintegrate. What I mean is that they actually turn into some other element. They become more stable as in a different form. The other thing you want to know about half-life is the symbol is T with a subscript 1/2. It's an example of exponential decay. Every element has its own half-life. Some are very short and some are very long. Look at this decay curve and I'll show you what I'm talking about with exponential decay. At time 0 on the x-axis, you start with 100% of your atoms. But after a certain period of time, one half-life, you're down to 50%. Basically all I did was multiply 100 by a half to get 50. After another half-life passes, 50 times 1/2 takes me to 5% of that isotope remaining. After another half-life, 25 times 1/2, I'm down to 12.5%. You can see the shape of this curve is decreasing exponentially. This happens naturally to elements that have unstable isotopes. You can also think about it in terms of percentages. I showed you the graph. The other way to think about it is to look at the numbers. The formula we're going to use to calculate the amount remaining, or NT, is to take our original amount, N sub O, and multiply it by 1/2 to the nth power, where N is the number of half-lives that have passed. So again, if I start with 100%, after one half-life I'm going to go down to 50%. Another half-life, I'll go down to half of that, or 25%. The next half-life will take me down to 12.5%, and so on. And this continues on until the isotope can't be detected. So for every one of these, a half-life has passed. What percentage of that technetium would remain after 1 day? Well, let's get our units to match first. 1 day, as you know, is 24 hours. Have passed in a total of 24 hours. Well, 24 divided by 6 gives me 4 half-lives. So this technetium will have gone through 4 half-lives. Now, if I use the formula that I gave you earlier, to find the percentage remaining, we are going to multiply by 1/2 to the 4th power. All I need to do is plug in my original amount here. I'm going to plug in 100% because that's the amount that I started at time 0. So if you do that math, 100 times 1/2 to the 4th power is what we're going to figure out. Have to use that little caret button on your calculator. You end up with 6.25%. 6.25% of this technetium should be remaining after 1 day. So it's great for use in the medical field because it doesn't last in your body that long. Now, is this right? You can look at the slide before this one. After 4 half-lives, what we found out, that lives
3.5%. So I think we did this problem exactly the right way. Let's look at another example. In this one we have an isotope of molybdenum, and we are trying to figure out how much of this 1 milligram sample will be left after 335 hours. So the first thing we need to do is figure out how many half-lives is 335 hours. I'm just going to divide because I know that 1 half-life for molybdenum is 67 hours. That's given to us there. So 335 divided by 67 gives me a total of 5 half-lives. So the molybdenum goes through 5 half-lives. Let's use our formula to figure out how much of it would be left.
Now we have a 1 milligram sample to begin with, because
remember 5 half-lives. So again, in your calculator, we're going to do 1 times 1/2 to the 5th power. And how much I get left is 0.0313 milligrams. Again, you can go back to the slide that looks at the percentages and you'll see a similar thing here. But this time we're in milligrams and not in percentages. So that one's correct. Let's do another one. Carbon-14 is probably a radioactive isotope you have heard of before because it's used in archaeological dating. They actually date samples from these Chinese temples. You may have seen pictures where they found all of the soldiers that had been carved. They're trying to figure out the age of those using the carbon-14 isotope. In this example, we're not given milligrams, but we're given counts per minute. It works the same way though. They identify the radioactivity using something like a Geiger counter or a scintillation counter. Those are just instruments used to detect radiation. So the first thing we need to figure out is how many half-lives has this sample gone through to decrease to 8.125 counts per minute. I'm going to take the 32.5 and divide it by 8.125. Every half-life, the counts will half, just like the milligrams will. So this is really going to be worked the same way. You find out that this sample has been through 4 half-lives. If it's been through 4 half-lives, and each half-life is 5,715 years, we need to figure out the age of this artifact. Well, if 1 half-life is that, we want it to go through 4 half-lives, so that's going to be a lot of years. I'm going to multiply by 4, and we find out that these artifacts are 22,860 years old, simply by knowing how the concept of half-life works. Alright, let's go again. This time we have a sample of iodine. Now iodine is going to be used a lot in the medical field. It's used for thyroid tests, for example. Here we're trying to figure out how much of 100 grams of a sample will be left after 32 days. Okay, so I'm going to be able to plug into that formula that we used earlier. Times 1/2 to the n power. Now my original sample is 100 grams, so I've got that. I know I'm going to multiply by 1/2. I need to figure out how many half-lives 32 days is. So I'll just go over here on the side. The half-life is 8 days, and if I'm looking at the sample for 32 days, that's a total of 4 half-lives. So I'm going to use 4 here as my exponent. Do that math and you'll be able to figure out how much of that 100 gram sample remains. 100 times 0.5 to the 4th power, that gives me 6.25 grams of that iodine. What that means is 6.25 grams is still iodine 131. The other 93.75 grams has decayed into some other more stable element. It is still there, it's just not iodine 131 anymore. So why do we care about all of this half-life and radioactivity information? Well, the answer, quite frankly, is energy. You know from already taking a history class that the United States has made use of this concept during the World War when we dropped the bombs on Japan. Those were atomic nuclear reaction bombs. So take a look here at the reason that that bomb was developed. When an element forms, this is oxygen for example, you know every oxygen has 8 protons and 8 neutrons. I know the mass of 1 proton and I know the mass of 1 neutron. So what I did here is I calculated the mass of an oxygen atom. What happens though is when an atom forms,
there's something called mass defect that happens. In other words, the actual mass of an oxygen atom is not exactly the same as we predict by adding together protons and neutrons. A little bit of mass is always lost. So here's Einstein's famous equation, E equals mc squared. What Einstein figured out is that if you take that change in mass and multiply it by the speed of light squared, you can calculate the amount of energy that that process releases. For an oxygen atom, it would release 1.23 times 10 to the 10th kilojoules per mole. Now, how much energy is that really? Let me give you a comparison. Let's compare that oxygen atom, or that mole of oxygen, to burning 1 mole of methane gas. Burning 1 mole of methane gas gives us 810 kilojoules. Burning 1 mole of oxygen gives us a lot more. In fact, it's over 15 million times more energy from that nuclear reaction forming the oxygen atoms than it is burning that methane gas in a normal chemical reaction. So that's really why we care. Nuclear weapons, of course, have applications from this, but so does nuclear power. Now, there are a lot of other applications for nuclear reactions. We've already talked about some examples where nuclear dating of artifacts has been used. We looked at an example where they use isotopes for medical testing. We talked about the energy and the weapons that have been developed as a result of Einstein's work. What I'd like for you to do to finish up this project is to get online and research a couple of these uses and applications.
Find some specific isotopes and figure out how they work. If you're really interested in medicine, look those up. If you really are interested in World War II and history and the Manhattan Project and how the bomb was developed, look that one up. I'm not going to assign you a topic. I just want you to look and see some of the uses of these reactions, because obviously we can't do nuclear reactions in lab, so I want you to see how far the technology has come. See you next time.